For centuries, a question about something we see every single day sparked one of the biggest battles in the history of science. Seriously. And the answer, well, it completely changed how we see the universe. So what was this epic fight all about? Let's dive in. You'd think the question would be simple, right? What is light? But for hundreds of years, the smartest people on the planet had two totally different, completely opposite answers. Finding the truth is this incredible scientific detective story, a quest that really pushed the limits of what we thought was real. The entire debate really boiled down to this one single conflict. Is light a stream of tiny microscopic bullets, or is it a ripple moving through space, kind of like a wave spreading across a pond? Particle or wave? In one corner, you had the heavyweight champion of science, Sir Isaac Newton. He argued for his corpuscular theory, basically light as a bunch of tiny particles. And in the other corner, you had the underdog, Dutch physicist Christian Huygens, who had this wild idea that light was actually a wave. Now, for more than 100 years, Newton's fame alone meant pretty much everyone went with the particle idea. And get this wasn't some quick debate that got settled over a weekend. I mean, look at this timeline. The basic ideas were being tossed around back in the 1600s, but it took almost 200 years of incredible experiments to finally land on an answer. It was a true slow-burn revolution in physics. So how did the underdog wave theory finally start to win out? Well, it all goes back to the absolutely brilliant idea at the heart of it, cooked up by Christian Huygens. Huygens' whole idea starts with something called a wave front. And the best way to picture this is to just imagine dropping a stone into a calm pond. You see those perfect circular ripples spreading out? Each one of those rings, where the water is at its highest point, that's a wave front. It's a line where every single point is moving together in perfect time. Okay, so here's the really clever part. Huygens figured out a way to predict where a wave would go next. His principle is actually pretty simple. He said that every single point on the edge of a wave acts like its own little mini source, creating a tiny new wave. The next position of the big wave is just the line you can draw, connecting the edges of all those little baby waves. It's a beautiful, geometric way to map out a wave's future. And this is where the debate got really interesting, because the two theories made a clear, testable, and totally opposite prediction about the real world. Newton's particle model said that light should actually speed up when it enters water. Huygens' wave model said it had to slow down. They couldn't both be right. Someone just needed to build an experiment to see who was telling the truth. And then, in 1850, Leon Foucault did exactly that. His experiment was ridiculously precise for the time, and the result was just undeniable. Light travels slower in water than it does in air. This was a knockout blow to the particle theory and a huge, huge victory for Team Wave. So, Foucault's experiment was a major point for the wave theory, but scientists still needed that one final piece of evidence. You know, the smoking gun. An experiment so clear, so undeniable, it would settle this whole thing for good. And that brings us to the climax of our story. A British physicist named Thomas Young knew that waves have this one really weird superpower. When two waves crash into each other, they can either add up to make a bigger wave, or they can completely cancel each other out. It's called interference. And here's the key. Particles just don't do that. So if you could make light interfere, you'd prove once and for all that it's a wave. His setup was just brilliantly simple. He took a light source, passed it through a single tiny hole, and then let that light go on to pass through two more tiny holes, or slits, that were super close together. That first slit was a clever trick to make sure the light waves hitting the next two slits were perfectly in sync with each other, what physicists call coherent. So let's just pause for a second and think about this. If light was just a stream of tiny particles, like Newton thought, what would you expect to see on a screen placed behind those two slits? You just expect to see two bright lines, right? One lined up with each slit. Simple. But that is not what Young saw, not even close. Instead, he saw this bizarre, incredible pattern of alternating bright and dark stripes. This was it. This was the smoking gun. There is absolutely no way for particles to create those dark spots, places where light hit light and made darkness. So what in the world is going on? Well, it's all about how the waves interact. The bright stripes are where the peaks of the waves from both slits arrive at the same time. They add together, they reinforce each other. That's constructive interference. But the dark stripes?
That's where the peak from one wave meets the valley of the other wave. They completely cancel each other out. Total annihilation. Only waves could do something that strange.
So Young's experiment was a total game changer. The debate was over. And now that the wave theory was the undisputed champ, scientists could finally start explaining all kinds of other weird and wonderful things that light does. One of those things is diffraction. You know how you can hear someone talking even when they're around a corner? That's because sound waves bend. Well, it turns out light does the exact same thing, just on a much, much smaller scale. It literally bends around corners and spreads out when it goes through a narrow opening. And the connection between interference and diffraction is actually super deep. In fact, the legendary physicist Richard Feynman once said that nobody's ever really been able to find a meaningful difference between them. Interference is just what we call it when a few waves are involved, and diffraction is what we call it when there are tons of them.
Another key discovery was that light waves are transverse. Now, what does that mean? Well, imagine you're shaking a long rope, up and down. The wave travels forward, away from you, but the rope itself is just moving up and down at a right angle to the direction of travel. That's a transverse wave, and that's what light is. And this one fact explains another really cool property.
And that property is called polarization. Because light is a transverse wave, its vibrations can be oriented in different directions, up and down, side to side, or any angle in between. Now, light from the sun or from a regular light bulb is what we call unpolarized. Its vibrations are all over the place, totally random. This is where something like a Polaroid filter comes in. You can think of it like a gate with tiny vertical slots. Only the light waves that happen to be vibrating vertically can wiggle their way through. Everything else gets blocked. So that first filter takes random unpolarized light and turns it into nice, orderly, polarized light. And then you can use a second filter to control it, even blocking it out completely if you turn it the right way. Okay, so we've been on this huge journey, from Newton's particles to Huygens waves, but what's the big takeaway? Why does all this fundamental physics actually matter in our everyday lives? Well, it turns out the applications are literally everywhere. Those polarized sunglasses you wear to cut down on glare from the road, they're using the exact principle we just talked about. 3D movies use polarization to send a different image to each of your eyes. That beautiful rainbow of colors you see on the back of a CD or Blu-ray disc, that is pure diffraction. The wave nature of light even sets the absolute physical limit on how much detail our most powerful telescopes can ever see. And that, to me, is the real magic of this story. A centuries-old scientific debate about the very nature of light is the bedrock for technology we use every single day. So the next time you put on a pair of 3D glasses or see a rainbow on a soap bubble, just remember the incredible journey of discovery that made understanding it possible. It really makes you wonder, doesn't it? What other huge scientific mysteries are out there right now, just waiting to be unlocked, ready to change our world in ways we can't even begin to imagine?